That is cool. I really like the universal parabolic constant. This was the last time that I was saying universal parabolic constant today. No, obviously I have said it another time, but this really doesn't matter because I really like the term universal parabolic constant. Try to say it out loud 10 times in a row and summon Mr. Beast today to your closet.
A huge thanks to Brian for sponsoring this video.
Good morning, fellow mathematicians. Welcome back to part 2 of most certainly 3 on the parabola. I know, Papa Flammy, parabola. It doesn't sound exciting, but watch the first part. You are most definitely going to learn something new. It has to do with conic sections and like a new form of the parabola that you probably have never heard of before, using the so-called focus. And what we're going to do today is we are going to derive ourselves something that is hiding in plain sight. It has been hidden in plain sight for all of us for years, but you never noticed. The universal parabolic constant. It's a constant that holds for each and every parabola that you can quite possibly think of. Doesn't matter if you have a parabola like this or maybe a hard-open parabola. It really doesn't matter. It's everywhere, it's freaking cool, and one of my most favorite constants ever. So definitely watch the video until the end for the amazing solution. It's really cool, I promise. Has a lot to do with integration. It's nice. By the way, this video has been sponsored by the wonderful people over on Brilliant. More information at the end of the video. And now we are going to dive right in. So at first, a tiny little reminder what happened last time. What we did is we defined ourselves a parabola, not by being in its usual vertex form. No, what we did, we grabbed ourselves a focus and we defined the parabola as being the set of all points, which is equal distance away from the focus and the so-called directrix. That's not the x-axis, that's the directrix down here. And what we defined ourselves is the focus as a point which under translation lies exactly here for each and every parabola that you can quite possibly think of. And we can rewrite the parabola in regular vertex form as being like this, where f is our focal length, which is just the distance from the focus to the vertex of the parabola. Okay, so this was a little introduction, and it really doesn't matter which parabola you take. You can also rewrite it like this, because under translation, each and every parabola is looking like this, kinda, where the relationship holds that our focal length is equal to 1 over 4a, where a is our stretching and also mirroring factor, right here on the vertex form. And now we are going to make use of our focal length once again, namely 2 times the focal length, which is just the direct distance between our focus and the directrix. We are going to call 2 times the focal length p. And what we are going to do is we are going to divide the part of the parabola which is stuck underneath our lattice rectum by our focal parameter p. And this division, this quotient of this line segment and p is always equal for each and every parabola. And this is the universal parabolic constant. I'm going to refer to it as UPC because it's a bit easier to say than universal parabolic constant at all times. So what is the UPC? It's being denoted as capital P in books if you look it up. And it's just a division of this line segment underneath the lattice rectum and the line segment connecting our focus with the directrix. Now, we know the value of this thing down here. This is p, which is the same as 2 times f, but we know what f is. F is nothing other than 1 over 4a. So 2 times f is the same as 1 over 2a. And if we plug this in, we are going to be left with this line segment divided by 1 over 2a, or in other words, this is 2a times the length of this line segment. And how do we find out the length of a line segment of a function? Well, obviously with a line integral, and this is what we are going to do. But to do so, what we need at first is obviously the bounds for our integral, and the bounds for our integral are exactly here for each and every parabola in the coordinate system. Namely, we are going to look for the intersection between the function, which describes our lattice rectum, and our parabola. Now, if we drop this down here, we are going to get 2 roots out most definitely all the time, because the focus lies inside over the vertex of a parabola. Now, this right here is x1 and this right here is x2. And now we are going to see what the equation for the lattice rectum is. Well, if we take a look at this sketch right here, it's just a constant function, basically. And this constant function is exactly at the height where our focus is, namely c plus 1 over 4a. So our lattice rectum function can be defined, I'm going to call it capital L for lattice rectum, as c plus 1 over 4a. And now to find the intersection points, we need to just set it equal to the equation of a parabola. Now, this right here includes a, so I'm going to go with the vertex form because all of those are equivalent anyways. So we are going to set it equal, namely a times x minus b squared plus c is equal to c plus 1 over 4a. And now we are going to do math. Not with e, but with a. We are going to subtract c on both sides. We are going to divide both sides by a. It's non-zero, obviously, because otherwise it would be a constant function, not a parabola, giving us overall that x minus b squared is the same as 1 over 4a squared. Now by taking the square root and after that adding b on both sides, we are going to be left with two roots exactly, x1 and 2, being equal to b plus or minus, and this is a squared obviously, because we divided by a. And if we take the square root of that, we are going to get 1 over 2a out. Okay, nice, done and dusted. Those are our two roots of our polynomial that we found out here. In other words, the intersection points. And now we can plug all of this into the line integral. Now, if you, just a little bit of theory, I have derived this equation before on my cycloid video, I think has been years ago, years and years ago. But if you want to find the length of a line segment L of a function, what you do is you take the integral from x1 to x2, it's a line integral, of the square root of 1 plus the derivative of your function squared, and integrate all of this with respect to x. And this definition we are going to use now on this line segment. Now, let's get started, shall we? The universal parabolic constant can be described as 2 times a times the line integral from our lower bound is going to be b minus 1 over 2a in this coordinate system right here. Obviously, the negative branch lies more to the left, since a is positive in our case, but if a is any random arbitrary real number, it really doesn't matter, just change it around. So this gives us b minus 1 over 2a, 2b plus 1 over 2a, and now the square root of 1 plus. And now we are going to take the derivative of our function. The derivative of our function, a matter of fact, you can use this one right here for the integration because the length of this line segment does not change, or the ghost blackboard. The length of this line segment does not change under translation, obviously. I mean, this line segment is the same here and here and there and also down here. Really doesn't matter. So you can make use of this, but I want to show, just for clarification purposes, that it holds for any arbitrary random parabola in vertex form. So we are going to differentiate this. So this right here is going to die in Mexico. It's going to vanish using the chain rule, dragging the 2 to the front. Gives us 2 times a times x minus b. Okay, perfect. And now this right here screams trig substitution. You could introduce yourself, for example, the tangent, and then you are going to get the secant square out by the fundamental theorem of trigonometry, and this is going to turn into a mess, if I'm not mistaken. Anyways, what I used for my derivation was a hyperbolic substitution because they are a bit easier to handle in the normal case. So what I'm going to do is I'm going to take a look at the fundamental theorem of trigonometry for hyperbolas, I think. I don't know if there's a real name for that. Namely that the cos squared minus the sin squared is equal to 1. And by adding sin squared on both sides, we are going to get that 1 plus sin squared is the same as cos squared. And then the square root of the cos squared is the absolute value of the cos. We are just going to go with the cos instead of the absolute values to make our life a bit easier. So clearly, an easy way to do substitution here is by sharp looking at it and by introducing the substitution. Let the thing in our parentheses, namely 2a times x minus b, be equal to the sinh of t. Now differentiating this, and this is the cool thing about hyperbolic substitutions, because they are kind of like trig substitutions with sine and cosine. The differential of the sinh is the cos, of t dt. If you introduce the tangent as a substitution, you are going to get the secant squared out, which is 1 over the cosine squared, and this is going to turn into a mess here, so don't do it. And here, differentiating this part with the b is going to vanish, and x is going to vanish too, so the only thing left is 2a times dx. Now the cool thing is, 2a times dx is exactly what we have here. So we can directly substitute it for cos of t dt, giving us that the UPC is equal to the integral from something to something. We need to plug those into here, and then we are going to see what we are going to get. But other than that, inside here we are going to get 1 plus, and by definition this is going to be the sinh squared of t times the cos of t dt. Now if you plug our upper and lower bounds into here and solve for t, obviously what we need to do is we need to take the inverse function of the sinh on both sides, which is the area hyperbolic sine. So we are going to get that a sinh of, and then 2 times a times x1 and 2 are only differing by the plus or minus before the 1 over 2a, so this is b plus or minus 1 over 2a minus b. Now you're going to notice that the b and negative b is going to cancel out, and 2 times a times 1 over 2a is going to turn into the area hyperbolic sine of plus or minus 1, which is nice, I think. So we can plug this into here. I'm going to call this for now just T1 and T2 to make our lives a little bit easier. So from T1 to T2, if we plug this in, we can simplify this part right here. As mentioned before, we want to trace this back to our cos. So if we take the square root here, we are going to get the square root of the sinh squared plus 1, which is the same as cos. So this right here is the hyperbolic cosine of t. And now we are going to end up with the integral of the cos squared. We are going to go through it step by step. As always, I like to derive stuff here on this channel live during the video. I'm not liking to grab most of the stuff we have done previously, because someone could come into here who hasn't watched my previous videos, and then he sees how you can go about it. Now what we are going to do is we are going to do just simple integration by parts. We need something to differentiate, something to integrate. Obviously we have both times the cos, and if we differentiate this, we are going to get the sinh out. Now multiplying this and taking the integral of this part, we are going to get that our universal parabolic constant UPC is the same as cos times sinh, evaluated from T1 to T2 obviously, and then minus the integral of the sinh squared dt. Now, what is sinh? Sinh is the same as cos squared minus 1, exactly. So this part right here is the cos squared minus 1. And now, what we can do is we can basically split this up. So we are going to get negative the integral. So this is cos times sinh from T1 to T2. We're going to get negative the integral of cos squared dt, and then we are going to get plus the integral of dt. Now you're going to notice something. What is the integral of cos squared dt? This is exactly what we got here. But what is it? It's our universal parabolic constant. So this part right here, and this is basically Phoenix substitution, Phoenix integration, because you can get your original integral back. Obviously those are from T1 to T2 at all times. This right here is P, and if we were to add P on both sides, we are going to get an expression for 2P being equal to cos times sinh from T1 to T2 plus this integral right here, which is fairly easy. This is just T evaluated from T1 to T2. And this is where we are going to continue on the next blackboard. Let us continue. So most of the stuff is fairly easy to evaluate. Now you could grab yourself a calculator, for example, and you're going to find out that on the one hand, the area hyperbolic sinh is an odd function. So it doesn't matter if you have it on 1 or -1, you just track the corresponding sign to the very front, giving you both times the same value, just with differing signs. And you can derive yourself the equation for the area sinh pretty easy by using the regular definition of e to the x minus e to the negative x over 2. And then if this right here is your sinh, you're just going to grab yourself the inverse function. You're going to get a logarithmic expression out. I have done it here on this channel several times. It's very easy to evaluate. Long story short, the a sinh of 1 and also thus negative 1, 2, just with the differing sign, is the same as the natural log of 1 plus square root of 2. So this part over here is going to turn into the log of 1 plus square root of 2 minus log 1 plus square root of 2 is 2 times log of 1 plus square root of 2. Okay, so this part right here is done. Now we need to handle this part. And the cool thing about inverse functions is if you apply it to their corresponding original functions, you are just going to get the argument out. So this part right here, evaluated at a sinh of 1 or a sinh of negative 1, is going to turn into plus or minus 1. Now we just need to handle the cosh of the a sinh. And this is also not hard if you remember what we have done a second ago. Namely, that the cosh is nothing other than the square root of 1 plus the sinh squared. Now, by the same arguments as here, what we can do is we can plug our area hyperbolic sine into here. That means if we have the cosh of the area sinh of plus or minus 1, what we are going to get is the square root of 1 plus the sinh of the area sinh of plus or minus 1, and all of this squared. Now, the inverse function applied to a function is just the argument in and of itself, and plus or minus 1 squared is always positive 1, which is going to turn into the square root of 1 plus 1, which is the square root of 2. Okay, perfect. So in each and every case, this right here is the square root of 2. Now we just need to handle the first and second part of integration. For the first part, this is going to be positive 1 times square root of 2, which is just square root of 2, minus, and then we are going to get negative 1 times the square root of 2. It's the same logic as here. So negative square root of 2, which is the same as 2 times square root of 2. Or in other words, 2 times the universal parabolic constant is 2 times the square root of 2 plus 2 times the natural log of 1 plus square root of 2. And by cancelling out 2 on both sides, because 2 is not equal to 0, it's a successor of 1, we are going to get the final expression for the universal parabolic constant being the natural log of 1 plus square root of 2 plus square root of 2. And that's it, my boys and girls. The universal parabolic constant. And I think that was a really fun ride, and I hope you did enjoy what you have seen today. And if you want to see more parabolas and stuff like this, maybe analysis, integration and the like, then I invite you to try out the contents of today's sponsor Brilliant, who are kind enough to sponsor yet another video here on this channel. Holy Lord, there was a mouthful. So many singes, area, hyperbolic sines, and also universal parabolic constants. But that was a lot of fun, at least in my opinion. And it's crazy that a result like this just lies in plain sight somehow, that at least the ratio of those two things is always equal for each and every parabola. And this is just a cool way to define yourself such a geometrical figure. And there are many more geometrical facts out there that you have probably never heard of. And Brilliant might be the perfect place to learn about something like this today. Brilliant, with their nearly 70 interactive courses in all topics STEM, be it the mathematics that we did today, physics, computer sciences, etc., is some of the best online learning content that you can find out there on the World Wide Web. Their app is also great. You can learn something new on the go. But point is, if you want to learn something new on a daily basis in any STEM field you can quite possibly think of, for example, physics and general relativity or mathematics and Markov chains, then Brilliant is most definitely a source that you could use to get further in your studies in no time at all. And when I say no time at all, I seriously mean it. I have often used Brilliant for myself too during my studies at university and now in school, and they are great visualizations to learn something new that I haven't heard of before. For example, in the computer sciences courses, when I learned Python back then in CS, it was completely new for me and I sucked at that. But with their kit that they are using, you can use those building blocks and start programming. It was really easy to understand the syntax of Python, for example, and how I can use certain orders of commands to get the results out that I was striving for. It's seriously awesome, it's seriously brilliant, pun kinda intended I think, but the best way to experience it for yourself is by trying it out today for completely free by using my link at the top of the description, brilliant.org/flammablemavs. 30-day free trial of amazing awesomeness. Try out the whole landscape of Brilliant for completely free and see if it's something for you. And if you feel like this could turn into a long-term relationship between you and their product, namely their interactive courses, then definitely make sure to make complete use of my link here down there in the description or the QR code somewhere up here in the corner and get 20% off an annual premium subscription. It's seriously worth it. They're adding so much new stuff on a regular basis. Christmas is kind of around the corner, so they are probably going to come up with some great Christmas special over there too. So definitely make sure to check it out and learn something new today on a daily basis, forever, hopefully. And this concludes today's video, and I hope you had as much fun as I did, because I certainly did. That is cool. I really like the Universal Parabolic Constant. This was the last time that I was saying Universal Parabolic Constant today. No, obviously I have said it another time, but this really doesn't matter because I really like the term Universal Parabolic Constant. Try to say it out loud 10 times in a row and summon Mr. Beast today to your closet. And this concludes today's video. I thank you guys for watching and have a flammable Universal Parabolic Constant day. See ya.